introduction. I'm Fabrizio Montesi. Choreographic Programming. What it is, by like holder, I'm going to about that. I think we need the background for systems. We have multiple things happening at the same time. What we are interested in is understanding the amount. A few weeks ago, research section was out for a social lunch. Is a big robotic was being served by robots. When we had the human there explained the rule to us, and he told us, please don't order the food at the table, because if you do, then there's not going to be enough space at the table. It's very reasonable advice. We had all the options of following it. Tablet could use to order food. It's all you need. It was so simple. You just and robot. Just too much for some of us. But it was much for some. They saying compulsive rapid tap disorder. Both managed to keep up with it. So food, scamming, everything was right. But we realized the road is me through exactly this. What do you think the other robot replied? Right. We were witnessing a deadlock. Obviously, nobody programmed, or at least nobody programmed correctly, this particular, right? Displayed by the sad face. Which probably very complicated. So this is a very toy example for a single sound. This is W where the client would like to look at, and an authenticator process A. So the client wants to log in through the authenticator process at the web. Explain the code. It's very simple code. It's a toy example, as I said, but we all know that predicting the behavior of concurrent code is pretty complicated. So I don't want to waste a lot of time doing that. And it's complicated because it starts looking like this very easily. You have to start matching which messages are going to be consumed by which other processes at which point in time, and then you follow the internal control flow of each program, and then what this triggers, which then gets received by another process, and so on and so forth. Okay? Now, this thing, which looks circular almost, I would say, but it's not. It's actually very, very simple, right? And the aim of choreographic programming, if you like, put very simply, is that what is simple should also look simple. If you have simple communication behavior that you want to implement, then your program should express it in a very simple way. Some of you might be familiar with this principle, you know, keep it simple, stupid, right? But I think what we are building as a community in choreographic programming is even better, because a lot of people are aiming at elegance in their papers and the abstractions they're building. So I'm going to upgrade it for the purpose of this talk to the chef's kiss principle, if you like, which I'm going to depict like this in the slides. We are going to cook a lot of eggs. So even before choreographic programming, people have been writing choreographies. They're just not programs, right? But when you are interested in specifying or documenting what kind of communications you should have, well, people have been using for many years message sequence art, sequence diagrams, notations inspired by workflows and other graphical notations like automata. Most of the time, it's usually natural language that people express choreographies, but unfortunately, I suspect the vast majority of cases, choreographies are just in the heads of developers, which are trying to form this puzzle across all these programs that they're coding. Because it's a bit in the way, you know. Once you have written a choreography that is just documentation or a specification, it's an additional artifact that you have to make. You haven't coded anything yet. We know this is a bit of a fool's errand. We have overwhelming anecdotal and empirical evidence that even expert programmers make a lot of mistakes very easily when they code concurrent systems. So this doesn't work. Dark times. Where do we look for inspiration? Well, choreographic programming starts from the premise that if we accept that communication is so important to the programming of concurrent and distributed systems, then we should make an abstraction for it and represent it in a manifest way in our programs. Let me draw a parallel with functional programming. If we accept that functions, the function abstraction, so defining a function and calling a function, it's so important to programming, then what would you rather have? A low-level language where then you have to prove manually or verify somehow that, yes, this piece of code is indeed a function definition, and yet this piece of code actually calls the function? Or would you rather program in a functional programming language that actually gives you syntax for defining a function and calling a function, call it a day, literally? The same we are trying to do for choreographies and expressing emerging behavior. The inspiration coincidentally comes from a notation that is very familiar to people doing a functional programming, right? But this is not the function type. It's not logical implication. It's a notation to express movement of data from a participant A to participant B, which started from the security protocol community. Actually, I'm going to argue later in the talk, it started even before. To avoid any confusion, although I am going to show you that it's actually intimately linked to what you're used to in logic and functional programming later on, I'm going to write for the names of the participants lowercase p's and q's because they are actually process identifiers. So I'm going to read this as the process P communicates something to the process Q. How do we use it? And this is what you typically do in a choreographic programming language. I'm going to use a simple imperative one. I'm going to rewrite the previous example, the single sign-on example we had. So you use it like this. You write, the client C sends some credentials. Credentials is a local variable at the client to the authenticator process A, which stores the credentials that it receives in its local variable X. Then A makes a choice. It reads like a normal programming language, but computation is located, and you have this communication abstraction up there. So if the authenticator process thinks that the credentials are valid, then it communicates the decision OK to the web service, and the web service generates a session token and communicates it to the client C. Otherwise, the authenticator tells the web service the credentials are not valid, and no token is sent to the client. The idea in choreographic programming is that once you have a choreography like that, a program for your entire system, or at least for a part of your system, then you run it through a compiler which generates the code for each participant. And this is exactly the same code I showed you before for the participants, for the three processes. What is the key difference? The key difference is that what was very complicated to look at now looks simple, right? These are exactly the same two flows represented in traditional distributed programming or in a choreography. In the choreography, you can clearly see that first we have the communication from C to A, then A makes a choice. If the choice is OK, then the web service releases a token, right? It takes a moment to see this in the choreography. It takes much longer to see it in the concurrent program. So we're following our principle. All right, one of the key properties you want to establish when you do choreographic programming, and choreographic programming is not just limited all the time to just compiling code. There are many other interesting aspects that I'm going to talk about later, but in the typical incarnation of choreographic programming, you have this compiler. What do you want as a property? You want the compiler to be correct. It's normally established by modeling the choreography language, the process language, and then you show some operational correspondence. One of the most typical properties that you get for free out of the correct compiler is deadlock freedom, which Marco and I here elicited in this paper around 11 years ago. So the idea is that since in a choreography, at least in a language like this, you do not write send and receive actions separately, but you only have the communication abstraction where basically you express the entire thing atomically, that C sends and A receives, you can never mismatch. It's syntactically disallowed to mismatch send or receive actions. Right? So the choreography can always progress, and by correctness of the compiler, the system can always progress. Right? And the fact that you get this for free without even needing a type system for simple choreographic language is a staple of the paradigm. How do you use choreographic programming? Well, here are a few examples. There are more, but these are the main ones. You can write an application as a choreography, compile it, and run it. You can get skeleton code, so you project some code. The projection is just another way, choreographic programming lingo, or choreography lingo in general, for saying compile, typically, because you project the choreography on a specific process. So you compile choreography to a process, then you get the communication behavior, but you can add details later on. And then you can use the usual method from round-trip software engineering to keep the two representations in sync, choreography and the processes. Or lately, and this has been getting a lot of traction in the past 4 years, I would say, we have choreographies as libraries. So the idea is that you wrap the code you get out of a choreography, and there are principled ways to do this, right? In functions or methods. And for example, here this says that given some credentials, you get an authentication result. You get a method that you can invoke at the client, right, from the choreography. And then you can use this library to code an application that uses it to participate correctly in a protocol. Now, choreographic programming has many phases. I've just shown you one. I can't show you all of them in detail. It would take far too long. But I thought of making a little timeline because it's important to be aware of where they come from and where we are going, in a sense. It starts in 1978, when these two people published a very important paper. Does anybody know who they are? Answer only if you know both. Does anybody recognize them? Somebody needs a security course. Almost. Nope. Yes. And then the other is? Yes, exactly. It's Needham and Schroeder, the authors of the very famous Needham-Schroeder protocols. Now, Needham and Schroeder, they published the first paper where this notation has been used, the A arrow M colon M, meaning A communicates to B the message M, right? They use it like this to describe a protocol for secure authentication that they want to propose. I was very, very curious about where they got the idea from. And then to try and figure it out, I read their paper, and all the papers decided, but some papers are not available online, so it was very hard to do. So at some point, I just bit the bullet, and I wrote to Mike Schroeder, right? Who, by the way, also has one of the coolest profile pictures. Anyway, Mike was very kind. He replied very, very quickly, and he told me that he was quite sure that that paper was the first one where they, with the notation for encrypting messages by using a superscript notation, like this one. But about this notation, the arrow notation, he wasn't quite sure. So he suggested, because this is such, he wrote, it is an obvious way to present such protocols, of course. So he suggested that I contact his PhD advisor, Jerry Salter at MIT. And I did. I was on a kind of, investigative journalism frenzy. So I wrote to Jerry Salter, and Jerry replied, saying something interesting. So first of all, he checked all the papers I couldn't access online. He actually had them, and they do not present that syntax. And second thing, he said, I have a foggy recollection that people were using this notation already in discussions for early internet protocols in the 70s, right? That's where my investigation stopped. I talked to many other people. I haven't figured out exactly where it comes from yet. But many people even don't care, because Jerry agreed, and many other people that I talked to agreed, that, yeah, it is an obvious way of expressing what's going on, right? Now, as a language designer, when I hear obvious, self-evident, clear enough times, I think of this. We are following the principle. So that's what started it all, in a sense. Another landmark, I'm going to jump forward to 2005. Okay, it's a big jump, lots of stuff happened. It's a very incomplete timeline. People developed all sorts of formal methods to reason about concurrent systems, some very successful. But what is special about 2005 is that it is a sort of reminder and representative event, because the W3C, the World Wide Web Consortium, they published the choreography description language. This is a choreography language for specifying, describing the expected interactions of a system of web services. Now, I'm not so interested in the language per se, which was, by the way, incredibly innovative for the times. This being the 2000s, everything had to be done in XML, you know. So this is how our wonderful, simple primitive looked like. Okay, this is the XML of P sends X to Q, which receives it in Y through the operation by over a session channel K. But if you pay attention, I said session channel, there's a notion of a channel. There's a notion of operation. I mean, these people knew what they were doing. Because at the time, for the past year, I mean, in the 2000s, it was a remarkable decade of interaction between the web services community and the community of concurrency theory. And especially the community of process calculus, like the pi calculus and so on and so forth. They love making syntax for expressing and studying concurrent behavior. Marco suggested to me, maybe even too much sometimes. So lots of models and semantics of choreographic languages, which were not yet choreographic programming, but without them, I'm almost sure we wouldn't have this paradigm today. We got that, and also the very famous multi-party session types method out of these studies. So that's why I put it there. It's a bit of a good reminder of why having different communities interact can bring good things sometimes. In 2013, jumping ahead, I proposed in my PhD thesis that we have a paradigm, actually, a programming paradigm that merits consideration. We should really take it in itself as an interesting thing and study it. I did it because of a few things, of a few observations. I'm just going to give some representative examples. One is that together with Marco, not only did we discover that you have this very interesting liveness property for free, but also the abstraction comes with interesting laws. And one very interesting law is the law of independent communications. If you have two communications in sequence, P1 to Q1, P2 to Q2, so independent processes, completely parallel. Since P1, Q1, P2, and Q2 are all in parallel, they can communicate in the order they want. So if you have, this is equivalent to swapping the two communications, because we can predict the order in which they will happen. It's an example of out-of-order execution at the choreographic level, when independent processes do independent communications, you can do them in any order. This law comes from the semantics of parallel execution in process calculi. So it doesn't just pop out of thin air. We didn't just make it up. Well, we did formulate it. We made up the formulation. Of the semantics of time process. Another reason is that I meant to implement choreographic programming. I think it was a bit like the right place at the right time. The theory of choreography at the time was heavily based on, so it was projected to and was I developed a programming language which was so very easy compilation. In a sense, it focused on really hard problems, which was how to model channels at the time. But it was nice because we went away from lots of theories, we could and get executable for architecture. So a big jump. Another and final reason I'm going to present for this is that we found a deep link to logic. We knew at the time, because of the proofs-as-processes agenda between pi calculus and linear logic, the proofs in linear logic correspond to processes in a simplified version of the pi calculus. Propositions correspond to session types for these processes, and that if you follow the process of cut elimination of a proof, you get to see the communications enacted by the processes that correspond to that proof, by the process that corresponds to that proof. But if choreographies are syntactic descriptions of communications, then they should have a place in here. And we did find that place. If you follow the process of cut elimination of a proof, well, that is exactly expressible as a choreography, syntactically. So choreographies, they give you a syntax for expressing a process of cut elimination. And what's better is that we got two things. One is a syntax for pi calculus-like choreographies. This is P communicates to Q over channel X and new channel Y. And we got a confirmation that our law is there also in linear logic. One of the most interesting features of linear logic, some say the most interesting feature, but I'm not going to push there, is that when you do cut elimination, some cuts can be performed independently. They are concurrent, in a sense, right? And we could see that. We could see that when you can perform a cut reduction, basically our communication abstraction, it corresponds to a cut reduction that you have to do, and you will be able to do. When you have two communications that are independent, so two independent cut reductions that you can perform them in any order. Exactly the same law. And that's why I thought that we should give the paradigm a name and we should start studying it for real. Another jump, 2020. Together with Saverio and Marco, we end a struggle, I would say, of how long? 3 years of development, something like that. It was a pretty long road. But we managed to finish Choral, an object-oriented choreographic language. This is the first choreographic programming language integrated with a mainstream paradigm, if you like. In this language, what we did was take in Java, because we wanted to prove that you can really use choreographic programming in the real world. And we extended Java in a very simple way. You annotate a data type with the process it is located at. So this method now reads, given some credentials at the process C, you get back an authentication result at the web service. Now we can express this kind of stuff with a very simple addition. Well, if I can express that, you can express this. This is a communication method. Given data of type T at P, it returns data of type T at Q, right? So we can reconstruct in object orientation the communication abstraction. We don't have to add it as a completely foreign thing. It just comes out naturally of this extension. And then you can write choreographies like this. This is like you have a number 42 at P, you communicate it, and now you have the number at Q. And you can write choreographies like this. I'm not going to go into the details of Choral. There's a presentation at PLDI on Wednesday, if you're interested, held by Marco and Saverio. But what Coral really contributed is that you can use it. It's a single language for any application of choreographic programming known so far. Well, the last one, I think it started with Coral, arguably, because you have this principled way of getting the types for the libraries from the choreographic types. Oops. And it solves this very important problem of programming in the large. We didn't know how to program in the large with choreographies yet, because we didn't know how to wrap them and encapsulate them. And this is the language that introduced that. Now, when we saw that this programming in the large was important, that the Coral data types were so powerful, we started getting interested in, well, can we really understand the foundations of this? This is in parallel with the work that Andrew did together with Deepak Garg. We had basically an intention of investigating how do we do the same to lambda calculus to understand really the essence of this. And the idea is very simple. It actually scaled very well, or downscaled, if you like, from object orientation to lambda calculus. You annotate types with processes, and then you can have primitives like this. Come from P to Q, give me some data of type T at P, and I give you data of type T at Q. This is the communication primitive in lambda calculus. You just add it as an axiom to the semantics and type system that whatever data you give it, it returns the same data on the other side. Then you can write choreographies like this. You start with a number at a process, 42 at P. You communicate it to Q, so now you have it at Q. You apply a local function at Q that transforms this number into something else, and then you forward the result to R. This is more or less how we program in Coral as well. Another landmark was Haskell, developed by Lindsay's group and Gan and Shun. Do we have Shun? Hello, Shun. Why is this so interesting? It's the first embedded choreographic programming language. It's the first language where people did not have to develop an entire separate compiler toolchain. They just took Haskell and made an embedded domain-specific language for expressing choreographies. And it integrates with the rest of Haskell, right? The communication primitive looks like this. P communicates the expression E to Q, so it looks very much like the primitive we are used to. And you can use the Haskell type system to track that everything is at the right location. Then what you do is that once you have formed a term that is a choreography, you just pass it to a function that they have developed that basically interprets it from the point of view of a process that you tell it, right? So it's a bit like the rest, but interpreted at runtime, and you get this very nice embedded DSL. The idea apparently scales because right away they applied the same idea to Rust, and we are getting more to come. And I know that today we are getting to see at least 2 other shapes of the choreographic abstraction, maybe more. I know that there's one for the Lispy lovers, and there's one where you don't even see the communication because you just infer all of them. Data just falls magically into place. What do all these phases have in common? Well, there's a principle of locality. Data and computation is located somewhere. There's an objective viewpoint. You look at all the processes you have from above. And there's the interaction abstraction with its laws. So these are some of the key features, perhaps the key features of choreographic programming languages. Now, since we are at the Choreographic Programming Workshop, I thought of reporting on some terminology. There are a lot of interesting problems, a lot of interesting theoretical aspects of choreographic programming and choreographies in general. These are particularly interesting. I call them the translational questions. So when you go from choreographies to processes, there are 2 questions, those on the left. One is called realizability. This is standard terminology also from previous works on choreographies from long ago. So given a choreography, does there exist an implementation of it in terms of processes? To give you an idea of why this might not be the case for all choreographies, consider this one. Here I have a process A that makes a choice, and then if the choice is true, for example, another process, a web service, needs to communicate a token to the client. Otherwise, we communicate something else. This is not realizable because that web service doesn't know what to do. The choice is made by another process, A, so the information about the choice lives there. We say we have a problem with knowledge of choice. I'm going to show you later how to fix that. A stronger question is that of projectability. It's the computational instantiation of realizability. So it doesn't just ask, given a choreography, is there an implementation? It asks you to compute it. Can you compute an implementation of this choreography? Of course, projectability is strictly harder than realizability. Here you need to provide a mechanical answer, right? So you need to give me a compiler, for example, that will do it. In between all of these questions, there's an interesting fix, the one that I promised you for realizability, which is called amendment. Amendment is a transformation of a choreography. You give it an unprojectable or maybe unrealizable choreography, and it's an automatic transformation that returns a projectable one. So for example, amendment would realize that this doesn't work because there's some missing information from A to WS, and inject the necessary communications, as in the example I had before. So there are very sophisticated methods to do this automatically. Going the other direction, from processes to choreographies, the expressivity question, which I'm just dubbing, by the way, people have not really thought about that a lot. They mostly mention extraction, but I thought it nice to give the same symmetric view on all of this. Given a process or an implementation, can we write a choreography that describes it, right? This is an extremely interesting question. I'm going to talk about it a bit more later. It's extremely interesting because, for example, well, choreographic languages are usually deadlock-free. So, of course, there are processes you cannot express. But are they interesting at all? We don't know. The computational equivalent. So, given a system of processes, can we compute a choreography that describes it? And here there's a stream of papers, and people have been very successful at it, at least for processes without non-determinism. But still, processes with recursion, there are very strong results about. So if you want to get into semantics of choreographies, I had the terrible idea of writing a book so that people could tell me all I get wrong. But I really tried to be friendly to beginners. Maybe that's why I get so many people telling me about typos, especially students. It follows the structural operational semantics approach by Plotkin. More on that later. And I tried to distill from all previous work why compilers work thanks to very strong algebraic properties in theory of projection. Okay? Now, why am I following the semantics approach? Because all we do normally in choreographic programming papers, at least about the theory of it, is proving these operational correspondence results, right? And essentially what we're proving are bisimilarity results between choreographies and the code we compile out of them. And if you follow the methods in the book, you will basically get a bisimilarity. You just apply the proof in there, and you get a bisimulation. So if you want to get into these kind of questions, the laws of abstraction, of the interaction abstraction, and so on and so forth, I would also really recommend reading Davide Sangiorgi's excellent book on bisimulation and coinduction. Now for something entirely different. So I've been talking about why we need choreographies from a technical viewpoint. But a few years ago, I was contacted by a few art curators. Our university is wonderfully covering many, many disciplines. And I was contacted by these art curators to make an art exhibition about choreographic programming. I bet you don't hear this often in talks. So I thought it was a terrific idea. Let's do it. I had no idea what I was jumping into, right? And Marco and Saverio kindly accepted to help. What did we do? We were having workshops with artists, some very well-established artists and art curators with a lot of expertise and experience, and tried to tell them about choreographic programming, what it is, what is its essence, and so on and so forth. The artists went crazy with it. We had choreographies of fiber optics where you had particles of light interacting with each other and forming different patterns. We had computers talking to each other. We had a plant in a feedback loop with a screen, and they could communicate with each other. The plant could change the color of the screen. And we had a giantography of a choreography that I tried to explain to the public, right? But the idea is that people really liked this intuition of being able to talk about how things interact. This is not so far from what artists do, after all. We had a real choreographer, like somebody who actually does it in art as a full-time job. And she designed a choreography for citizens. So you come in as the public, you get some headphones, and it gives you the projection for you, essentially, of what you're supposed to do. There's concurrency in it. There's orderly structures. And in the end, they all join to see what the heck they have realized together, right? Which was not evident until that point, to elicit the difference between your local behavior and the global emergent behavior that you get. You can see it. It's upcoming now. It's been running for a while. It's coming to Sweden, Denmark, and Germany soon. Now, at the event, long story short, we had this discussion with the public. And what really struck me is that from high school students to senior citizens, they were really engaging with this idea of understanding a bit more what was happening between computers communicating with each other. And in particular, they wanted to know, can we use these methods to understand how our data is used on the internet? So I did what any serious academic would do. What do you think? Bravo, Matteo. I started drafting a grant proposal. I got in contact with Claes de Vries, a colleague at our university, who is also one of the best political communication scientists you can find. And we started writing this grant for the Willem Foundation, which is now running. This is a project that's running right now. So I don't have a lot to report yet, but it's already giving us a nice nugget of information. In a workshop with users, we asked them to look at a protocol using a sort of natural language notation, right, to express a communication, or the arrow. And my expectation was that the arrow would lose and they would prefer this notation. And instead, there were a lot of people who wanted the arrow notation. I don't know how else to say it. So, just to, last thing I'm going to mention is that there are still a lot of things to understand about choreographic programming. We are starting a big project. It has just started in June, this big project at the University of Southern Denmark, funded by the European Research Foundation. What are we going to work on? Well, one is reasoning techniques. We want to develop logics to understand and reason about properties of choreographies because, there are a lot of advantages from doing it on that level where the order of interactions is more manifest instead of concurrent code where it's much harder to get. Expressivity, there are still a lot of classes, entire classes of concurrent behaviors that we cannot capture in choreographies, especially when you start having difficult levels of non-determinism like networks losing messages around and exceptions or crashes and stuff like that. So we want to explore that. I've also told you that there's a very interesting question about realizability and projectability, right? Our compilers are simply not smart enough right now. There are a lot of protocols that make sense. They can, in principle, be given a distributed implementation, but the compiler is not smart enough to figure it out. So we want to change that as well, or improve on that. And development, we want to make it easier for people to develop choreographic software in the real world by using our results. Now, these are very connected, these three endeavors. Just to give you an example, without going too much into the details, there are logics out there, especially model logics, to reason and model concurrent behavior, right? So you can use those logics, and since we have a label transition system for choreographies, you can, for example, immediately use a Henderson-Miner logic, just to give an example, to write the specification of a behavior, and then you can ask yourself if this is inhabited in a given choreographic language or not, and you can establish separation result, for example. So lots of synergies. What is interesting for the community, which we are probably going to reach out to you about, is that there's an appalling need for organizing knowledge on choreographic programming, right? Especially the newcomers, they struggle with what are all the papers I should read, and we need to be better at that. So this is something we should probably do together as a community. Everybody is developing new choreographic languages. Everybody is adding a primitive. This is starting to become a process calculi 2.0. We are getting a zoo of choreographic languages. I'm completely fine with that. That's probably necessary. It was necessary for process calculi, and it's still necessary. However, I really started wondering, can't we do sooner than people did it for process calculi? Can't we start developing generalized theories with maybe intermediate choreographic languages such that people can compile to those? It's much easier to compile to a choreographic language from a higher level choreographic language rather than directly to the processes. And this we plan on formalizing in a theorem prover. We call it MEC, mechanized choreographies. And lastly, we need a benchmark. We need to systematize how we compare languages, how we evaluate these languages. There is nowhere to be seen a table, I can dream, a table showing me all the important features that I need to care about for each class of concurrent behaviors that I should care about with representative examples. It's not just us, there are multiple communities who could use this, including the community of session types, the community of process calculi, the community of multi-tier programming. So maybe this goes even beyond choreographic programming. But we really need one, so we should work on that. And that's all I had to say. Thank you very much for listening to me for so long. Yes?
Can I just yell from here? Fantastic talk. Is done? Okay, fantastic talk. Thank you so much. Really liked it. I'm really an outsider to the community, but it's beautiful. So maybe slightly beyond the reach now, but what's the story of choreographic programming in a Byzantine setting when not everyone is going to obey
We haven't reached that yet. So I'm just going to guess. What the best we have so far is right below. So we have a model still unpublished, but it's been going around for a while now. Where everything can fail, basically. Send actions can fail, receive actions can fail, so send and receive omissions. And then we also have omission failures, like where the network can lose a message, right?
Can there be confounding messages?
Can they become what?
Confounding? I think that's the terminology when someone sends the message out of order, but it's in principle like in the protocol, so it's not corrupted, it's just bad.
Yeah, well, we don't, basically what we are assuming is that there are no corrupt messages. There are, if there is a duplicate, it's because you actually wrote the code that generates the duplicate and stuff like that. So that we can handle. But if a process, and we can still guarantee degree of freedom through a type system, which is much simpler than what one might expect because of the overall view the choreographies give you. But if we have somebody behaving maliciously, then we don't know. And I guess, actually, this has been a long-running thought for a while. So first, we had to do the omissions that I'm talking about. And the plan for after that is to go back to 1978, or rather a bit after that, maybe. But we know choreographies or protocols, like in many different settings, that can deal with the Byzantine setting, right? So the idea then is, can we make a choreographic programming language expressive enough to model those protocols, right? And that would be the next step. But it is certainly an open question and a very exciting direction.
Is this on? Can you hear me?
No.
Yep.
Is it online?
Hello.
It's just for the online people.
Oh, it's only for the online people. Okay, good, good, good.
Well, we can hear you.
So where do session types fit into this picture? Should we dispense with session types? Just use choreographic programming? Do they complement one another?
Well, there's at least one paper where they complement one, well, multiple papers.
What's your view going
My
forward?
My view is that you should definitely keep both. Otherwise, I would never dare to be so arrogant as to, no, but seriously, scientifically now, we're talking scientifically, I would never be so arrogant as to say that I can predict that we can get rid of any of them. We don't know if choreographic programming is ever going to be powerful enough to capture everything, and we don't know if we can ever get rid of lower level languages where session types operate. But I know two things. One is that history tells us we should keep both. We are still running with C code. Session types are going to be fundamental to integrating a lot of unsafe code in the future with maybe choreographic code. Second thing is that you can use session types to type choreographic programs, which we've been doing for a while. And you can use that as interesting interfaces when you project the code, for example, and now you have the library generated from a choreographic program. Well, maybe now you have the library generated from another choreographic program. How do you integrate them? This is still an open question mark. We had some answers using session types. We are probably going to have many more using separation logic and what's not, right? And maybe people you will use extraction to compute the overall choreography of all choreographies in your program. But who is to know which approach is going to work best? I think lots of fun stuff to do in all of these topics, to be honest. So definitely don't stop doing session types because Fabrizio gave a keynote at Choreographic Programming in Copenhagen. Thank you. Sure.
Yeah, thanks for the talk, Fabrizio. Just one quick question. Are there things that you can't do with choreographic programming?
The short general answer is no, because, but I'm cheating, right? We know that there are a lot of interesting choreographic programming languages where you can mix the communication abstraction with low-level actions, right? Like we did in the logic paper. So you can interleave a communication and then put an action towards the environment. If you can do that, you can probably model a lot of things. I don't have a formal proof, but I would definitely try to see if it is possible. Can we model everything just using the communication abstraction? This is a bit like, I guess we'll know when we see it. Just like they do in physics, you know, in theoretical physics. That's the answer they typically give you. What is important there, I think, is the benchmark. But you know, first maybe the concurrency theory community should figure out a process calculus that can express all concurrent behaviors. And we don't have an answer for that either. So it would be nice to have one. Turing completeness we have also for choreographic programming, but it's obviously too coarse as a property. Beautiful question.
Hi, wonderfully presented. Can you hear me all right?
Yeah.
So the work in choreographies reminds me a little bit of work in things like program partitioning, where you automatically take a single program and divide it up into multiple computing components, or even work in high-performance computing, like the languages like X10, where there's an explicit, and now you move to this machine, keep going.
Yeah.
How do you see these various fields as all relating?
Right. I'm not familiar enough with the technicalities of these paradigms. I'm of course familiar with them and that they exist. We did once a comparison with multi-tier programming. There's a difference in how you write code. For example, in multi-tier programming, you don't have this objective viewpoint over the whole system. You jump instead from the scope of one process. You write some local code, and then you can jump to the scope of another process. So the view is always subjective, but you can hop from a process to another. You can, for very simple choreographic and multi-tier languages, you can translate back and forth, right? So the advantage of choreography is that you see the protocol that's going to happen. The advantage of multi-tier is that you can focus on one process at a time, in a sense. When I think about parallel computing especially, I think there are probably very strong connections because we had a lot of interesting results modeling parallel algorithms with choreographies. So then it depends on what you think a process is, because this is a choice you make when you apply choreographic programming. And that's where I would maybe spend some time thinking about. I think that's a very interesting question. So I don't know what the answer is, right? But these processes can be any kind of thing. So if in your hardware you have something that behaves like an independent unit of computation, then you can say that's a process, and then you can write the choreography of how they interact. We could use that even for generating hardware in principle.
Yeah, thanks for the nice talk. I'm a bit curious about the choreographies, because the way you presented this paradigm is still limited to kind of point-to-point communication, and the choreography is emerging basically from those. Now in high-performance computing, where this problem of send-receive has been also discovered some decades ago, the point was to allow specification of larger, let's say, communication patterns. Have you thought about something in that direction as well?
Yes, I just haven't presented them, but you can find, but that's of course a very good point, also because people have written papers about it, so it is certainly relevant. There's work by different groups, including ours, but also others, on multicast, broadcast, scatter and gather. Actually, in one of the papers where we use linear logic, if you think, if you go beyond the duality, the relation that you use in linear logic to check for compatibility of two processes, there's a generalization of it to multi-party compatibility, and there you get primitives like scatter and gather quite naturally. Another follow-up.
Yes, a quick follow-up. You mentioned all the kinds of things that are well known in HPC, in high-performance computing, like scatter, gather, broadcast, and so on. Have you discovered any pattern in this context that is different from those?
No, because normally we go about it the opposite way. We look at what patterns are used in practice, and then we try to model them. I think this is also why we need the benchmark effort, because we need to start writing down all the patterns we have in choreographies to reach out to other communities and maybe check with them, do you have these same patterns? Do you have something more? Do you have something less? Stuff like that, because maybe it will lead to extensions. Maybe these people wouldn't have to reinvent some wheels if we already had the theory for some of that. Something very interesting that came up connected to these kind of things is that there's a work we did on using a type system to model the topology of a high performance computer, for example, such that we could check that a process communicates with another process only if they're actually connected, or they can do a scatter or a gather only if they're actually connected. It's very easy to verify these properties with choreographies, and you get a decidable type system. So I think there is value in modeling these in a language that everybody can understand, at least. And that's definitely another kind of all these communities. This is why I love this workshop. The point, I think, is that we got so much out of two communities interacting in the past, web services and concurrency theory. Now we need to go beyond. Now we are getting to programming languages and distributed systems, but it's still at the very early steps. So definitely something very interesting to look into.
Thank you very much.
Hi, great talk. It was really interesting. This is probably the same answer you gave to the multi-tier question, but just to double check my understanding, would it be similar with sort of the world of these like actor languages where you write an actor system in a programming language that then compiles to a distributed system? Would there sort of be a similar difference between that perspective and the choreography perspective?
So actor languages, as in Akka, for example.
Akka being a framework, but for example, if you compiled like Pony to a distributed system in theory.
Sure. I see. Actors, for me, live on the same level of processes, in a sense, because you're still writing the behavior from the point of view of an actor when you write the code. And then you have another actor and you write the code from the point of view of that. The primitives are a bit different. They are reactive, typically. But I think today, actually, there's a talk by Dan on how to compile something that looks like choreographies. Well, they are choreographies. They are just different from what I presented, to actors. It gets a bit different when you study the theoretical properties of that, I think, because in actors, people really go out of their way to avoid deadlocks by using reactivity, right? So I think in there, you would want to prove some other properties that you could very likely prove with choreographies. They would be the equivalent of deadlock freedom in process calculi. Only instead of avoiding deadlocks, you avoid, for example, messages never being consumed. These are the properties I would expect by applying choreographies to actor. That was a very difficult question.
The Byzantine behavior. Yeah, well, he got right to the heart of the hard questions, didn't he? Yeah, so my question is kind of related to that, I think. So one thing that that I don't know how to do yet is deal with writing down choreographies for systems where you have participants joining and leaving. And in particular, maybe you have some short-lived participants and some long-lived participants and so on. And I know this is, maybe not something that you can answer briefly, but maybe you could say something about, what hope is there for choreographic programming to be able to encompass that kind of a system? Or do you think that the answer is more like, well, we should just be writing short choreographies for the different subsystems?
I'm very lucky. I can actually answer the question because Marco answered it for me in one of our research talks once. You see these processes we have in Coral, for example. Imagine you could existentially quantify over them. Then you could write a method. Maybe a new process has just arrived. You get the identifier of that process in the result of the method, and it's existentially quantified because you don't know who it is actually. But now you get to code with it, right? And then you can change the dynamic topology of the network dynamically within the choreography. So that could be an idea. Another idea is that we start writing reactive choreographies. Choreographies that get triggered by some external event, and then you still get the process that has just arrived, and it gets dynamically instantiated through some semantics. Now I said I can easily answer the question. Of course, this is totally underdeveloped, not developed at all. but I think it would be very promising to look into. Now Sam disagrees. That's the face of Sam disagreeing.
No, I'm just I don't disagree.
Thank you.
I don't know. I'm just interested in how you would deal with aliasing in that situation. If you have these dynamically bound participants, how do you know that you're not creating a deadlock by accidentally coupling
in the interest of time? You could either verify it. You will need to look at the local code that triggers the choreography, right? So here, see session types and the software verification. They might come in handy as well. Another thing that I think we should really look into is runtime checks. So if it's very easy to check that you have bad aliasing at runtime. And it's so far, for example, in Coral, the beautiful thing is that it doesn't require any middleware. But we have not investigated at all yet what happens if we start coding a middleware in Coral and using it, right? So implementing this check would be a natural way, and then whoever tries to join and you have bad aliasing, you get a fault, and you get out of there. Even more connected to that, if I can piggyback on your question, another very interesting runtime check is start having runtime agreement protocols where different programs, they check which choreographies they support, and they pick one at runtime, so that we can start having this at the level of transport, even, if you like, if you think about how to apply this on a large scale. So I think in general, this idea of performing runtime checks for compatibility, preventing bad properties from, or bad things from happening, etc., really has a future because it sounds very lightweight. Definitely lighter than performing a network communication anyway.
Thank you for the great talk. I think most of the work is based on network communication between nodes. And do you have any application for the low-level stuffs like place and routes and the processing elements, like for the accelerators, etc.?
No. We have, I mean, in Coral, even in the paper, you can find, for example, concurrent algorithms that use multi-threading. Because for us, if these P's and Q's are remote or they are on the local machine, Thanks.